Hello class, this is Adam Ward, and I want to talk tonight through the derivation of the line of action for our resultant force. And so you'll remember from class this is taking the distribution of forces and finding the equivalent if it were applied as a single point force. And the question was, where is that point of force going to be applied on a planar surface by a fluid? So what we're trying to solve is this equation, where on the left-hand side we see the resultant force F sub r applied at a location distance y sub r from the fluid surface, and that has to be equal to the integration of all of the incremental forces applied at their incremental areas. Now, in order to solve this equation, we can substitute our definition for force, specific weight, times depth, in this case y sine theta, that's equivalent to h, times the incremental area. We make that substitution. We can pull the two constant values, specific weight and sine theta, out front, and we end up with an equation that looks something like this. Now, we can realize that the term inside the integral is actually the second moment of the area. This is describing the distribution of the area about any axis, sometimes called the moment of inertia, and in our textbook this is abbreviated with a capital I sub x. That plus our definition of the resultant force, again gamma times hc times a, results in this equation. You see we've got a gamma sine theta on both sides. We can remove that from each side. We can simplify terms and find the coordinate of our resultant force through this equation. Now, we're not quite done yet. We can also think about this problem in terms of what's known as the parallel axis theorem. And the parallel axis theorem relates the moment of inertia about the centroid to the moment of inertia around any other axis. Formally, that parallel axis theorem is written like this, where the distribution of the area around the centroid can be corrected based on yc squared times a. That gives us the distribution of A about any axis of our interest. We take these two equations and we combine them, and this is the source of our equation for the resultant force. So we can take the resultant force, we know that it will act at the centroid as corrected by the moment of inertia around the centroid, divided by the y-coordinate of the centroid times area. To calculate those moments of inertia, IXC in this equation, you'll look at the table in Chapter 2 of your book. That is, I think, figure 2.13 on page 46 in your textbook. That's got squares, rectangles, triangles, circles, semicircles, any shapes that we're commonly going to need in this class. All of that to say, 3 minutes to deriving one equation that you need to know in the green box. Thank you.